Dear students, today we will study electric field lines. An electric field line is an imaginary line or curve drawn through a region of empty space so that tangent drawn at any point gives the direction of electric field at that point. It is a path followed by unit positive charge in electric field if it is free to do so. The relative closeness of the line at some point gives an idea about the intensity of electric field at that point. Properties of electric field lines. The field lines never intersect each other. If they do so, the two tangents can be drawn at the point of intersection, means two direction of electric field at that point, which is impossible. The field lines are perpendicular to the surface of the conductor. The magnitude of charge and the number of field lines both are proportional to each other. The field lines start from positive charge and end at the negative charge. For the field lines to either start or end at infinity, a single charge must be used. Representation of electric field lines. Four figures have been drawn below. So first figure is representing the field lines of your positive charge, and second figure is representing the field lines of your negative charge, and third figure is representing the field lines of one positive and one negative charge, and fourth figure is representing electric field lines of the system consisting of two positive charges. Now we will discuss electric flux. Electric flux is the rate of flow of electric field lines through a given area. The electric flux is proportional to number of electric field lines going through a virtual surface being held normal to field lines. If electric field is uniform, the electric flux passing through a surface of vector area S is phi equals E dot S, which is further equal to E into S cos of theta, where E is the magnitude of electric field having units of volt per meter, S is the area of the surface, and theta is the angle between electric field lines and the normal to S. For non-uniform electric field, the electric flux d phi through a small surface area ds is given by d phi equals E dot ds, where electric field E is multiplied by the component of area perpendicular to that field. Electric flux for different conditions have been drawn below. Flux is proportional to the density of the flow. Flux varies by how the boundary faces the direction of flow, and flux is proportional to the area within the boundary. Now students, we will state and explain your Gauss's law. So Gauss's law states that electric flux through any surface enclosing charge is equal to Q upon epsilon naught, where Q is the net charge enclosed by the surface. Mathematically, it can be represented as surface integral of electric field is equal to Q enclosed upon epsilon naught, where Q enclosed the net charge enclosed by the surface, and epsilon naught is the absolute permittivity of the free surface. If your surface is not enclosing any charge, then electric flux will be zero. Now students, we will prove your Gauss's law. So in Gauss's law, the surface integral of electric field intensity over any closed hypothetical surface called Gaussian surface in free space is equal to 1 upon epsilon naught times the net charge enclosed within the surface. So in order to prove your Gauss's law, we have to consider an isolated point charge plus Q at any point O. Suppose S is a sphere of radius r around the charge Q. Then the surface S is called the Gaussian surface, and the value of electric field is constant on your Gaussian surface. Now your Gaussian surface is further divided into infinite number of infinitesimally small surface element, and the flux which is coming out from the small surface element will be d phi is equal to E dot ds, that is equal to 1 upon 4 pi epsilon naught Q by r square r cap dot ds and cap. Therefore d phi becomes 1 upon 4 pi epsilon naught Q ds upon r square r cap dot n cap. Here r cap dot n cap will be 1 into 1 into cos of 0, that is 1. Therefore d phi becomes 1 upon 4 pi epsilon naught q ds upon r square. Now total flux can be calculated by integrating this equation. After making integration, phi becomes integral of d phi, that is equal to 1 upon 4 pi epsilon naught q upon r square integral over ds, that is equal to 1 upon 4 pi epsilon naught q by r square 4 pi r square, which is equal to q upon epsilon naught, which is your Gauss's law. Now students, we are going to derive your Coulomb's law from Gauss's law. In order to derive your Coulomb's law from Gauss's law, again, we have to consider an isolated point charge q lying at O. The electric field due to this point charge is radial everywhere, and its magnitude is same at all the points lying at the same distance from it. To find the electric field intensity at any point P at a distance r from the charge q, we have to draw a Gaussian surface. Now, according to Gauss's law, surface integral of electric field, that is equal to q upon epsilon naught, and the value of electric field is same on your Gaussian surface. And therefore, this equation becomes A into A is equal to q upon epsilon naught. Now, the surface area of a sphere is 4 pi r square. Now, using this value in our equation, therefore, E becomes 1 upon 4 pi epsilon naught q upon r square. For a point charge q dash at a distance r from the charge q, the force would be F is equal to q dash into E. Therefore, your force becomes 1 upon 4 pi epsilon naught q dash upon r square, which is nothing but which is your Coulomb's law.